Greetings everyone. The topic of our video today pertains to a paradigm shift in metallurgy, where scientists have weaponized corrosion itself to forge sustainable, ultra-strong alloys. Researchers at the Max Planck Institute for Sustainable Materials have re-engineered dealloying, a process once synonymous with decay, into a precision tool for crafting nanostructured porous metals. By merging dealloying and alloying in a reactive gas environment, they've birthed a carbon-neutral synthesis method that turns rust into resilience. Without further ado, let us delve into our discussion. For millennia, alloying, the marriage of metals, has driven human progress, from bronze swords to jet engines. Yet its shadow, dealloying, has haunted materials as a thief, leaching elements like oxygen and leaving skeletal ruins. But what if this thief could be deputized? What if the voids it carves became the blueprint for strength? The answer lies in science advances, where researchers unveil a method to harmonize dealloying and alloying using ammonia gas. By stripping oxygen from metal oxides while injecting nitrogen into atomic gaps, they've crafted porous martensitic alloys, 28.9% lighter than conventional metals, yet hardened to 36.9 HV Vickers hardness per gram per cubic centimeter. Ammonia plays a dual role, as revealed by Professor Dirk Rabe. Its hydrogen dismantles oxides, while its nitrogen infiltrates the lattice like a demolition crew that also rebuilds. The process begins with Fe2O3 hematite and Neo powders, cold pressed into pellets. At 455 degrees Celsius, ammonia decomposes, releasing hydrogen that reduces oxides to metallic Fe and Ni. Oxygen escapes as H2O, leaving behind a labyrinth of nanopores. Simultaneously, nitrogen dissolves into the lattice, distorting atomic arrangements to trigger martensite formation, a phase riddled with dislocations and nanotwins, 20-30 nanometers thick, that amplify strength. 4 pillars of synthesis, a single-step revolution one. Reactive vapor phase dealloying, hydrogen reduces Fe2O3, Fe3O4, Fe and Neo, Ni, excavating 27% porosity. 2. Substitutional alloying, Fe and Ni atoms interdiffuse, forming a uniform solid solution validated by EDS mapping. 3. Interstitial alloying. Nitrogen from ammonia occupies lattice gaps, reaching 3.0 atomic percent locally, APT data. 4. Martensitic transformation, rapid cooling, 120 degrees Celsius per minute, locks in a nanostructured martensite matrix with retained austenite below 1.5%. Thermodynamic treasure maps, Fig 1bc in the study, identify Fe, Ni, Co and Q as ideal candidates. Their oxides exhibit low oxygen vacancy formation energy, DFOVAC approximately 23 eV, and favorable reducibility, DG oxide, DGH2O 200 kJ/mol, enabling efficient dealloying. FIB-SEM tomography reveals a bicontinuous network, 94.1% interconnected pores, mean diameter 1.35 micrometers, and ligaments averaging 0.97 micrometers. Zener pinning from nanopores refines grains to sub-micrometric scales. Compared to melt-cast Fe 10% Ni alloys, 28.7 HV, the porous martensite achieves 36.9 HV at 5.69 grams per cubic centimeter, a 29% hardness leap at 28.9% reduced density. This method sidesteps carbon-intensive smelting, using hydrogen from ammonia as a reductant. The team envisions scaling with industrial waste gases, for example steelmaking emissions, and impure oxides. Applications span lightweight automotive parts, reducing vehicle weight without sacrificing crash resilience. Iron nitride magnets, EFE3N phases observed via in situ SXRD could rival rare earth magnets. Recycled alloys, upcycling metallurgical slag into high-value foams, supported by the Alexander von Humboldt Foundation and the European Research Council, Grant 10105486. This work redefines sustainability. As Dr. Xiaolu Wei notes, every atom has a role. Oxygen exits as water, nitrogen fortifies, and vacancies become strength. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.